Okay, for this lecture, continuing on with our topic of strain, we're going to look at strain and displacement. Now, in your previous lecture, the handwritten notes that had audio with them, we derived some very simple expressions for strain based on original length and final length, and these were all one-dimensional. However, that definition of strain is too simplistic for many of the applications that we really have to deal with. Our current definition of strain is just too simplistic, especially to represent strain in more than one dimension. Okay, for that reason, I want to take a minute here and look at 4 basic types of deformation. Okay, now recall strain is a measure of the rate of deformation. Now, type A we can handle with our basic definition of strain, okay, the stretching. But what about bending strain? That's where we automatically see now we have strain in more than one dimension and we have some curvature involved. Or twisting deformation. Now that's an interesting one. Okay, if you notice here the type of deformation. And finally, simple shear. Even though the term is simple, we can see there's a rather complex deformation that takes place here. With strain being a measure of the rate of deformation, we need to develop a more robust definition of strain and a more robust definition of deformation and displacement. So that's our goal in this lecture, is to start building a foundation towards that. But before we do, I also want to revisit Hooke's Law and talk about some of the limitations of Hooke's Law and how we're going to learn how to build on that basic Hooke's Law and develop a more robust representation of the relationship between stress and strain. Now on the right hand side you see a picture of Robert Hooke, Hooke's Law bears his name, and you'll notice it points out he was a scientist, an architect, and an engineer. Well, here we have the classic equation for Hooke's Law. Simply stated, stress equals Young's modulus, or modulus of elasticity, multiplied by strain. Now this is the simplest, absolute simplest equation representation of it. Now while this is a powerful conceptual representation that can be expanded in many different directions, this equation itself, as written, is very limited. It assumes a uniaxial state of stress, where stress is only acting in one direction, along one axis, a uniaxial deformation, where all of the deformation involved, again, occurs along only one axis, much like our simple derivation of strain that we did previously. It assumes the deformation is infinitesimal, and also that there is a linear relationship between stress and strain for the material. Now this is true of most materials as long as we stay below what's known as their yield point, or the point at which they become permanently deformed. At that point, Hooke's Law no longer holds, and we have to look at a plastic or more permanent deformation and laws and equations that have to do with that. But as long as there's a linear relationship between stress and strain. Now that's not true for all materials. For example, some of the shape memory alloys do not exhibit that type of a linear relation between stress and strain. Some materials it's an inverse. The more stress you apply, the strain is, well, let me just put it this way. The strain is not always linearly related. Okay. Now, there's a representation of Hooke's Law for shear also, which is good for us to keep in mind. Again, it's very limited in this, as expressed with this formula, but as basic concepts, very powerful. Shear is equal to a shear modulus, which is equivalent to our Young's modulus for normal strain, multiplied by tan alpha, which is a measure of the shear deformation or shear strain. Okay, so that's Hooke's Law, which we will be expanding on. But again, I want to re-emphasize to you guys that our definition of strain so far is very limited. We need a much better definition of strain, which means that we need a better definition of displacement. Okay, so that's where we're going to end this lecture, is our quick discussion of displacement, then go into some more discussions of strain. Well, here's what we're going to do. We're going to say when a body is deformed, every point in that body moves to a new set of coordinates. Now you can think of this as a volume of fluid being moved from one position to another under the influence of stresses, or a solid material. So here we have a solid material, and this is its starting point, A. We've got a point here in that material. We're calling it A. It's defined by a vector A. It's drawn from the origin to this point with components A1, A2, and A3. Now this point moves to a new position, x, defined by vector x with components as measured from the origin, x1, x2, and x3. Okay, so far so good. Our displacement vector, this was just position. Displacement tells us about the movement from one point to another. Displacement vector is u, and it's x minus a. Okay, it has these components. u1 is x1 minus a1. u2 is x2 minus a2. And u3 is x3 minus a3. And for our remaining discussion of strain, that is how we're going to define our displacement. Thank you.